Okay, I think it's time that we can start. Good morning or good afternoon, depending on where you're following this webinar. My name is Tadiscara Danelis. I represent the young engineering geologists and the IEG from as chair of the YEG. Today, I would like to welcome two presenters from Costa Rica, Professor Sergio Mora and geologist Mr. Randall Carballo Benavides. It's our honor that we're a multicultural group and we'll welcome attendees and keynote speakers around the world. So I will have a short introduction about our first presenter, Professor Sergio Mora. Dr. Sergio Mora holds a master's degree in geology at the Central American School of Geology, University of Costa Rica, and a master's PhD degree in engineering geology at the National School of Engineering Geology from Nancy, France. He's a professor at geotechnical geology in soil and rock mechanics and natural hazard assessment, and he works also as a project management at the Central American School of Geology in the University of Costa Rica. Since 1998, he serves as a consultant and professor on risk, environmental natural resources management, climate change, and engineering geology for various private firms, multilateral organizations, and several universities in Central and South America, the Caribbean, Middle East, North Africa, and Oceania. Professor Sergio Mora, I would like to welcome you. The space is yours.
Thank you. Can you please allow me to record the session?
Yeah, please feel free. I also would like to let know our attendees that our webinar is live streamed via the YouTube channel of YEG.
I think I need your authorization to make the recording.
Just give me a moment. I think it's
okay.
Allowed.
It doesn't matter. We can go on like this.
Okay. Okay.
We are recording, so no there's.
Yeah.
Okay. The topic that I would like to discuss with you today is it relates to the application of a heuristic methodology for slope and stability hazard assessment, and the application that we have produced at the Durango Mazatlán Highway in Mexico. The authors of this analysis were myself, as long as our colleagues Javier Saborío Bejarano, María del Mar Saborío, and Rosalba Barrios Díaz. Our client was Servicios Mexicanos de Ingeniería Civil, Caminos Puentes Federales, the Mexican Civil Engineering Services of Mexico, and federal highways and bridges of the government of Mexico. And we were under the supervision of Carlos Lopez, engineers Carlos Lopez, Victor Medrano, Arturo León, and Alfonso Rico, to whom we would like to take the opportunity to thank them for the opportunity given to us in carrying out this analysis. This, our methodology for slope and stability hazards is the one that we call the Mora-Vahrson method, was firstly published in 1993. It's already, we are already on their 28th birthday. We started with very rustic tools, even producing analysis of this kind by hand over 1 to 50,000 scale maps. Now, with the advent and with the advantages of geographical information systems and the algorithms that we can now use, we have come to use it as a very handy and efficient tool. This macrozonation methodology was homologated by the TC4 Committee of the International Society for Rock Mechanics, for Soil Mechanics and Geotechnical Engineering in 1999. It was published in one of the manuals of this TC4 committee. It is intended to be a low-cost, a priori system for landslide hazard macrozonation in tropical and seismically active areas, taking into account the fact that in developing countries, we do not always have access to sufficient, reliable, and with a high degree of resolution of data and information. So we intend this methodology to be a guide for initial decision-making processes, and where further and more detailed geotechnical investigation should be required. We want to underline or to hotspot areas where problems seem to be more evident, at least. Then it applies is the principle of the philosophy of this methodology is that we apply a set of morphodynamic proxy indicators which offer this orientation about the natural geotechnical conditions that prevail in the slope. And then we make a substitution of the geotechnical parameters. For example, we substitute the cohesion, friction angle, and pore pressure based on upon the lithological constitution that is determined by expert opinion, or if we have field data, of course, it becomes easier, as it was in this project in Mexico. The slope geometry is substituted by the relative relief index or the slope angle. The evolution of interstitial pressure, we analyze it from the prevalent moisture conditions that we will explain, and the accumulated precipitation in 24 hours, the intensity, duration, and frequency of rainfall. And then the seismic trigger we use to characterize it by the peak ground acceleration. In this case, we had the opportunity to use even a temporal ordinate to discriminate periods that we consider to be more damage prone for the slopes in these areas and seismic intensity, of course. So it is a spatial analysis, essentially. We define the slope and stability hazard parameter of composed by susceptibility and trigger factors. The susceptibility factors that we consider to be intrinsic to the slope are composed by the indicator of relief that could be represented by the slope angle or the relative relief index. The slope lithology susceptibility, which it tends to substitute the shear strength, and it is used by perception or determination, and the indicator of prevalent ground moisture content. And then the trigger factors are the ones that represent the influence of seismicity through its intensity and rainfall through its intensity, duration, and frequency. So the slope and stability hazard is defined by the combination of relief, lithology, prevalent moisture, combined with the seismicity and precipitation trigger factors. Of course, we can make iterations and enrich this methodology once the knowledge of the slope and stability situations is better understood, and also the influence of the trigger processes improve. The lithologic susceptibility starts with the determination, in this case deterministic, by the way, of the conditions of the lithology. So we make a basic qualification of the slope susceptibility by qualifying the rocks from the very low susceptibility, for example, massive, when they are massive with few joints, in case of limestones, basalts, granite, gneiss, and where discontinuities are clean and rough, and the water tables are low, and there is a low degree of weathering, a high shear strength. When the condition of the rock evolves into more fracture, more weather, and less shear strength, the susceptibility increases, and then the parameters decrease. In this case, as you see here, the same lithology, in this case, a pumitic tuff, gets weathered, and then the condition of the shear strength decreases. And then the rocks evolve and weather into residual soils or transported soils. And this same pumitic trough is shown here in a very fissured and weathered condition. So the susceptibility is very high, and then the influence on slope and stability conditions increase. We can add parameters when we do have the information to refine the classification, both in detail and spatial resolution. For example, by using the SMR and the Q methodologies, Wieniawski and Barton respectively, when we have the opportunity to qualify the rock condition on the slopes, we can add decimals to the qualification of the susceptibility of the lithology. And then we can even qualify the soils when they are residual or transported. And we do have information about cohesion and internal friction or uniaxial strength. So we can go into a higher degree of determination and discretization of the properties of the soil. So I can give you an example of what we have done here in Durango Mazatlán, classifying by symbol from the National Geological Map of Mexico, the composition, the hydrogeologic and physical-mechanical properties, the soil cover, in this case residual and or transported, and the determination and qualification of the SL factor and some characteristic features. So in this case, for the rhyolitic trough, which is Oligocene to Miocene in age, then we can describe the composition, the aspect, the physical-mechanical condition, the cover of soils, residual and or transported, and the determination of the parameter SL. That for the same lithology, it can go from a very low susceptibility, such as in here, where cuts are very stable, to a middle class susceptibility, such as in here, with the presence of water and springs, and to very high susceptibility when this stuff becomes very weathered. So this information was placed into a map, and from here, the lithological condition was analyzed in the highway corridor. And from the geological map, we established a reclassification with the assistance of the geographical information system to determine the spatial distribution of the lithological susceptibility condition. Then we also use the available inventory of slope and stability incidents in the highway to try to establish a first correlation with instability situations. The second parameter is the relative relief, which is defined by the maximum difference of elevation within a unit area of 9 square meters. So we use the focal statistic filter of RGs in this case, and we determine the Z values calculated with a mobile filter box of n by n pixels, in this case 3 by 3 pixels surrounded in the middle by a 9 square meter cell. So the filter passes over each cell. The center is assigned with an arithmetic function, which is elevated, maximum elevation minus minimum elevation. So, and the grid looks like this. And the subtraction of the maximum minus the minimum elevation goes along the displacement of this grid of 3 by 3 pixels. So, and then the way to determine each value for the relative relief surrounded by 9 cells. So, and then we make the classification of the relative relief, the way it is classified, or qualifies the slopes, and the assign SR factor. So, just to give you an example, this is a LiDAR segment obtained with 1 meter of pixel resolution. And the LiDAR map, in this case represented by the hillshade representation, is classified to determine the relative relief index and reclassify to obtain the final map that is used to classify the highway. So this is 2 segments of the highway Durango Mazatlán in Mexico. 2 different areas, one with a more or less semi-flat area, and the one that it crosses along the Cordillera in the western side of northwestern Mexico. Soil moisture is estimated through a hydric balance. It's the share of precipitation minus runoff and evapotranspiration. It tries to measure the infiltration that feeds the ground moisture, as we know it. Evapotranspiration can be obtained according to the context, the local climate, local topography, by using the Hargreaves relationship that takes into account a basic average precipitation and corrected by a coefficient multiplied by the elevation. Then we can obtain an annual range in millimeters and define an annual value of the soil moisture prevalent condition, and we made the qualification. So we can do that by month. Eventually, we can do that by day or by hour, if necessary, if the amount of data is sufficient, and it is as well its resolution and accuracy. And then we can do that again by quantifying the annual sum of the monthly indexes and qualify. So this is to analyze the highway. We have here the hydric balance map. You see the highway here depicted by the dots. And then the SH index, the soil moisture, the prevalent soil moisture and the highway. And then we can have here the highway corridor and some zooms to determine the spatial distribution of the prevalent soil moisture. So once we have lithology, relief, and moisture, we can make a linear combination of these indicators. And then the result is the susceptibility factor. I repeat, this is a combination of the susceptibility of the lithology, of the relief, and the prevalent moisture. And here is the result in 2 segments of the corridor. Then the triggers. We will see first the earthquake triggers. Mexico is, of course, a very active area, particularly the northwest. As you see here is the
fractures associated to both subduction and the fracture of Baja California. So we we were assisted by the ERN group with the crisis software and platform to estimate, you see here the highway in here, to estimate the earthquake trigger that we used with a certain amount of dots, points where the earthquake hazard was calculated. I'm not going to go into much detail, only to show that the procedure takes into account the geometry and the characterization of each of the pertinent earthquake sources surrounding the highway. And then the establishment of attenuation models for each of the sources. So, and then through stochastic procedures, they obtain the prevalent earthquake hazard according to different models, that usually the peak ground acceleration, but you could use also the modified Mercalli scale or any other classification that it is available. And then the definition of the value of the parameter of influence of the seismicity trigger. So ERN established in reality 5 basic scenarios. One that will be a subduction earthquake of 8.5 in magnitude momentum at 15 kilometers of depth with spectral, I'm sorry, this is 150 kilometers of depth with a spectral ordinate of 0.5 seconds with a 100-year return period and with 10% probability of exceedance. The second scenario was an in-slab subduction earthquake, reverse fault with a magnitude of momentum of 7.7, 30 kilometers in depth, in rock with spectral ordinate of 0.15 seconds and a 100-year return period and 10% probability of exceedance. The third scenario was an in-slab subduction earthquake, but at 10 kilometers of hypocenter, and the rest of the parameters were the same. In rock, spectral ordinate of 0.15 seconds, 100-year return period, and 10% probability of exceedance. And then the fourth scenario, a local earthquake of 5.6 in magnitude, momentum, 10 kilometers of depth, along or placed over, artificially over the highway corridor, and which represents the maximum expected value that can be reproduced by the available information in this region. And then the final scenario was a stochastic, combining everything, combining all scenarios and all sources, and to obtain, let's say, the largest earthquake hazard that scenario that could affect the highway somehow. And this is the scenario with the highway over it. It's always 0.15 seconds of ordinate, 100-year return period, 10% of probability of exceedance, and this is the highway corridor. This is the mountain area, the Cordillera, and this is the upper part of the highway in the Altiplano. Then the precipitation trigger. The precipitation trigger is defined by the fact that Mexico is under the influence of the cyclonic corridors, and this particular area was subject to several hurricanes and tropical storms in the last 20 to 25 years. So we can use the 100-year return period, 24 precipitation accumulated, or the 24 to 72 hours precipitation accumulated. And then we, with this, we can define the parameter of trigger of the precipitation. And this is a segment of the highway that it is shown in here. So when we do have susceptibility and each of the triggers, we can produce a scenario, in this case, an intense rainfall, slope and stability triggered by intense precipitation without an earthquake. There will be HP, the combination of relief, lithology, moisture, and precipitation. And this will be the scenario into segments of the highway. And then the slope and stability has a trigger by an earthquake during the dry season. Earthquake without rainfall. And then the resulting map. Finally, the maximum or the total slope and stability hazard triggered by an intense earthquake during the rainy season. Everything is involved: relief, lithology, moisture, earthquake, and precipitation. It is the reclassification score. And the two segments that we have been showing. And then to the right, we can see a correlation of the zonation with already known slope and stability incidents. Then trying to simplify the slope and stability index map to make easier the communication with the decision makers, we can produce, this is what we call a semaphoric representation with only 3 classes, from very low to nil, middle, or very high slope and stability hazard indexes. This methodology was put to text, to context and to test, and landslides that occur in areas where were already identified as with a high degree of hazard. We have others, but I prefer, we don't have the time to show all of them. Essentially, the methodology worked well. And then this is important that, to point out the influence of the topographical resolution on the degree of accuracy of the methodology. This is the corridor and the slope and stability hazard map with a digital elevation model of 30 meters of pixel available at the Geological Survey of Mexico on the website. And let's isolate this area of the highway. Well, as you see, you can see some details, and there is already some value that could orient decision makers. But when we compare this to the map produced with the LiDAR, with the 30 meter resolution, with the 1 meter resolution LiDAR map, you can see the same area. And the improvement, the significant improvement of the detail of the areas. You can even make a zoom here. And this is what it will be shown. There is, of course, a lot of room for improvement when you improve the hydrometeorological and geotechnical parameters as well, and the earthquake microzonation. There will be a significant improvement still to be obtained. And then we can, we propose this, but well, okay, this is a a scenario to assess the influence of anthropogenic global warming using the Mora-Vahrson method is a scenario that we produced later in the municipality of Esparza in Costa Rica. Considering the scenario that anthropogenic global warming might cause an increase on the IDF, intensity, duration, and frequency parameters in the long term, let's say in 50 years. We use that as a temporal horizon and increase the IDF function by 10% to assess the potential influence of anthropogenic global warming in case if this area will be exposed to a higher IDF multiparametrical new scenario. So you can see the increase in the amount of areas covered by the red, a very high hazard, and pinks, and particularly the change of condition of some of the cliffs that are nearby the coastal littoral area. And finally, we could even establish the possibility of using this methodology to orient a system of alert for slope and stability in areas, urban areas, or highway corridors, using the principle that we have just seen, the susceptibility parameters that are combined with the trigger parameters. And this could be in real time, in day, a month, a season of the year. Or in the case of rainfall, we could even have the meteorological forecast, either by hour or by the next 24 to 72 hours, or even the season. And we can have this information ready in ISO-yes, on IDFs, or the accumulated materials. And we can produce a forecast with the ex-ante condition to prepare the administration, the management of relief and rescue, or even maintenance in the highway or in urban areas. Unfortunately, earthquakes cannot be predicted, but we can have now very rapid information about intensities and the spectral response. So even if we cannot anticipate earthquake, we could have very quickly ex post intensity distribution, so we can orient the space and time distribution and the dimensions of the instability incidents to support safety, response, rehabilitation, reconstruction, and functional and operative continuity. Well, this is all that I do have to present. I will remain, of course, available for any questions that you might have. I don't know if the questions will be after Randall's presentation, or we do it right now. I am available anyway.
Thank you very much, Professor Mora Castro. I mean, it was really excellent, your presentations. I think the attendees really enjoy, especially what you mentioned with the advances in the geoinformation and in general in the geoinformatics. We can establish new methodologies and new assessment methods. As you already saw, the advance and the difference between the topographic data that you had and the LiDAR data had increased the result. Please provide your questions to the chat session. I think we can move on with Randall's presentation, and we can collect all the questions in order to be answered in the end of his presentation. So now I would like to welcome our YEG representative, Randall Carballo Benavides, who obtained his bachelor and graduate in geology from the Central American School of Geology of the University of Costa Rica. His thesis was on landslide risk assessment on highways, received an honoring grade. Since 2019, he works as an independent geologic consultant for small projects on Costa Rica. He has also participated in several congresses, both on national and international level, presenting his thesis. Since 2020, he acts as the Costa Rican representative for the YEG, and since 2021 as the secretary for Costa Rica Committee for Engineering, Geology, and the Environment. We are really happy to have you here, Randall. The space is yours. Welcome.
Thank you. Well, I'll begin. Well, first than all, good morning, afternoon, and night to everyone here. It's a great honor to have been invited. My presentation is called the HillSlope Quality Index Assessment on a Mountainous and Highly Vegetated Transportation Corridor. This project was my bachelor thesis, and I did it with the help of the National Laboratory of Materials and Structural Models of the University of Costa Rica. You might have the question of what is the HillSlope Quality Index, or HSQI? Well, it's a new pre-construction assessment methodology that determines the susceptibility to a landslide in a transportation corridor. It uses geological, geomorphological, and geotechnical data as inputs on a series of equations proposed by Chica, 1989, from the National School of Engineering of Nancy, France. This method is not mine. It was proposed by the master Carlos Arturo Moreno Ceballos in its master's degree thesis in 2015. What did we wanted to do with this project? Well, we have some things to consider. First, this method is new and is not tested enough. Its applications and limitations are not well known. And we don't know under which criteria can it be applied or if it should be modified. So what we wanted to do is to determine if the HSQI can be used in a forensic way on an already built highway, highly vegetated, weather and mountainous corridor. How does it work? Well, you, a decision maker, you have your area of interest and you want to build a highway on it. And you want to assess the landslide susceptibility that this highway will have. So what the HSQI proposes is to divide this highway in several sections. Each section will have a width and a length. The width is the length of the slope as seen from above, perpendicular to the direction of the highway, and the length can be said in different ways. It can be a specific distance, each section to be 150 meters long. It can be the length of a lithological unit appearing in your area or of a geomorphological unit. Or you can set a section each time your highway will have an inflection point. Each section will be analyzed to gather geotechnical data such as cohesion, friction angle, unit weight, and joint inclination and depth. The geometry of the slope, we want the angle and the height of it, and the water table height. I say height because the method measures it from the bottom of the slope upwards. So we have our parameters, right? Again, cohesion, friction angle, unit weight, slope inclination and height, phreatic surface height, and joint depth and inclination. These last two, of course, if they are in your slope. These parameters will be used in a set of equations. We have 12 equations that are divided. Allow me a moment here. All right. We have 6 equations for a translational or a structurally controlled landslide, or 6 for a rotational landslide. These sets are divided in X equations, from which we have 6. You're going to choose an X equations depending if your slope has no water table, has water table, or you have water flowing through the slope. And our Y equations based on the joint reality. You might have no joints, you can have joints, and your joints can be filled with water. So to apply the method, you won't use all 12 equations. You are only going to use 2. So you study your area, you go to the field, you do your remote sensing, and you determine what kind of landslides you're going to have. So to put an example, we're going to say that we're going to have, or we expect, a rotational landslide. And for the sake of simplicity, let's say that our slope has no water table and no joints. So we gather all the data and we run the equations and we get one x value and one y value. Why are they called x and y? Well, because they are the axes in these graphics, okay? The coordinate resulting from those two equations will tell me if my section and the slope on it has low, medium, or high susceptibility to landslide. And depending where the coordinate falls within this graphic. So where did we apply this? In the national route number 32 of Costa Rica, also called Braulio Carrillo. This highway connects what is the central metropolitan area of the country with the Caribbean shore, where a lot of important ports are. This highway had LiDAR information gathered thanks to the government. We can see this light green shade here. That is the area that has a LiDAR information on it. And this particular region on the country has high amount of precipitations. On map C here to the right, we can see the blue polygon that represents 7,000 millimeters of year in the sun. This data is from 2004. And as the rest of the country presents a high amount of seismicity. Each point is an epicenter from 1975 to 2017, from magnitudes from 2 to 5.5. But why did we choose this particular highway? Well, besides the fact that it has LiDAR information, it presents a consistent problem of slope instability throughout the year. Several landslides or rockfalls create traffic and economical losses. From 2011 and 2017, a total of 5.8 billion colones were used, which is 8.3 million US dollars. From these, 360,000 US dollars were used on landslide or debris removal. With the LiDAR information, we were able to create a landslide inventory that allow us to understand where and why these landslides are occurring. Within the region with LiDAR information, we identified 142 landslides, which an 82% or 109 occurred inside the cuts of the transportation corridor. These landslides go from less than 1,000 square meters to more than 100,000, being the majority between 1,000 and 10,000 square meters. How do these landslides distribute, especially in the highway? Well, like this. Here in the map on the left, we have the gray polygon is the LiDAR information, and each red dot is a landslide. As we can see, there is a clear pattern here that I am following, that is the highway, and the majority of the landslides occur within it. So we wanted to understand which areas were the ones that presented a higher risk or a more critical condition. So we made a density map. To the right, you can see it. Each pixel is 1 square kilometer, and its value is the amount of landslides within it. As you can see, we found out several critical regions, such as this, with 12, 11, 7, 8, and 7 landslide within it. We also understood that as the great majority of the landslides are occurring within the cuts, the geometry of them is one of the main factors for its occurrence. So how did we apply the HSQI here? And here's where the assessment part of the methodology begins. We wanted to see if it worked as a forensic method, but it was conceived as a pre-construction method. So it's natural that the HSQI proposes the geometry of the natural slope, the one molded by centuries of erosion and weathering. But thanks to our inventory, we realized that the landslides occur in the cuts, human-made angles and geometry. The water table height has been previously used as 0.6 of the total amount of the height of the slope, but we know that underground water varies along the year, between seasons, if it's rainy, if it's sunny. So using a single height for it is not realistic. We also know, well, in our geotechnical parameters and studies, it is always wanted to have clean values, right? Of course, that is not always the case. We found out several difficult to test materials, both in situ and in the lab, that gave borderline values to extreme, cohesions too low, friction angles too high, that did not really, or that were not expected from those materials. And we had, or the HSQI proposes equations for slopes with no water table. But in such a rainy area, this is not really to be expected. So I had this question, what to do? I need to assess this parameter and see if it works. So I should apply it as it was originally proposed. But in reality, I have different things, right? I have to gather parameters from where the method is not telling me to. So what should I do? Should I modify the method for it to be more accurate, or should I apply it as it was proposed? So I just decided to iterate, do both. The method tells me to use the geometry of the slope, but I also use the one of the cut. It tells me to use a water table height of 0.6 of the total. I decided to vary it from 0.2, from 0.7, hoping that this will simulate how a water table changes, especially and across the year. The geomechanical parameters, unfortunately, were not the best from our test. So we ran some fits using lattice from 2010, and we also did a back analysis. And our equations, I decided to run a whole test of the HSQI using the equation that does not contemplate a water table, and then another one without it. So instead of only using the HSQI once and see if it was successful or not, we ended up applying it 41 times. We applied 41 times and divided the highway into 112 sections, which resulted in a couple thousand HSQI values generated. Of course, each graph was applied a susceptibility based on where the coordinates of the equations ended up. So to better understand all the different parameters and iterations of the method, I gathered them in 9 cases You can see here the combinations of parameters that each one use. Some use the slope with the laboratory parameters, some did not. From these 9 cases, the best result was the 9th one. And for the sake of time, I'm going to present this one because I don't want to be talking here 2 hours. So this last case was the one with the best accuracy. It set the highway to have a 21% low susceptibility, 48% medium, and 31% high susceptibility. How does this look? Like this. All right, we can see regions with low susceptibility, high susceptibility, and medium. But why do I know that this was the most accurate version of the HSQI applied, right? At the end, what the method is telling me is I guess that the method does based on the parameters and the weight I put on them or in the equations. So if you remember the landslide inventory we did, we just run a comparison. The idea was, if the method is telling me that I have a region with low susceptibility, I should see low amounts or no landslides. If it's telling me that I have high susceptibility, I should see a high amount of landslides. So we ran these comparisons, and we had several places where we had a good correlations between the method and the landslide inventory. We remember this area with 12 and 11 landslides that was correlated with a high susceptibility region, and some areas with a low susceptibility and a good correlations. Of course, it wasn't perfect. We had some areas with low accuracy, but in general, we could say it was a success. So, was successful to apply the HSQI as a forensic method? Yes, we did got a good result, but we had to modify it, right? If we had used the parameters, or if we had gathered the parameters from where the method was telling us, we will have gotten an inaccurate result. The best example is the geometry of the slope. If we had used it, we had underestimated the susceptibility of the highway, and thus we had to use the one of the cuts. From all the 41 applications of the HSQI, in general, we could say that the best cases were using high water table heights, the geometry of the cut, the geomechanical parameters gathered from a back analysis, and the equations did not really provide a significant change when we ignore the one that did not apply the water table. So comparisons and conclusions. Please take in mind that in this section, I'm going to be speaking about Sergio's presentation of the Mora-Vahrson and of the HSQI. So we have the Mora-Vahrson, right? As you saw, Sergio applied it on a transportation corridor. What were the advantages of the Mora-Vahrson here and in general? Well, the Mora-Vahrson is already a widespread and tested method with successful results. I'm going to go to this hyperlink that Sergio provided. Here we can see all the analysis applications of the Mora-Vahrson throughout the years. It's a large area coverage method, so you can use it to study a big region. Can use parameters obtained from remote sensing techniques. It doesn't need to be in situ analysis. It's an efficient tool to detect areas with high slope instability, where further local geotechnical investigations are required. does not require a higher degree of expertise in the use of Gs. What were the advantages and are of the HSQI? Well, it does not require the use of advanced software. I told you I applied it 41 times, which were 41 Excel sheets. So you don't require a big or expensive software, nor a high-end machine. It's quick and easy to apply once you have your parameters. It sectorizes the highway corridors along the determination of more susceptible sections prior to construction. And parameters can be obtained from lab, literature, or back analysis should you not have access to in situ tests. But nothing is perfect, right? The Mora-Vahrson has its disadvantages. It's for macrozonation. You cannot use it for microscales. You cannot use it for a single slope. Its efficiency might drop if areas with low rates of precipitation and seismic activity. It's not a methodology that predicts. The Mora-Vahrson will tell you where mass movements are of higher probability, but not which mass movements. It can be a landslide, can be a rockfall, a rock topple. It's not going to tell you which one is going to be. And it's highly sensitive to degrees of resolution and quality of the parameters. Disadvantages of the HSQI. Well, it's not tested enough. It's a new method, so we still don't know its potential and its limitations. It's high sensitive to the degree of detail of the parameters introduced. As an example, the geometry of the slopes does not contemplate triggers. So the method can tell you that a slope or section is of medium susceptibility. And when you have an event such as an earthquake of a strong rainfall, that section can actually be of high susceptibility. So the HSQI does not contemplate this. It's impractical for large areas as you will need to create several amounts of sections. And it might underestimate susceptibility when not closely considering variations in topography and slope geometry, as we saw in this case study. So conclusions, again, for both the Mora-Vahrson and the HSQI, heuristic methodologies are conceived based on a set of data to study problems by generalizing or grounding the characteristics of a terrain in wide areas and when data is scarce. There is no perfect universal recipe that fully considers all factors involved in slope instability situations and that could be used in different environments around the world. Knowledge of the intrinsic characteristics of slope terrains, a wide selection of a methodology, and the use of engineering judgment are of vital importance to obtain acceptable analytic results. Heuristic methodologies are useful to determine scenarios in slope where instability might occur. However, they are highly sensitive to the degrees of expertise of the applier, the epistemic uncertainties, and the intrinsic variability of the geological setting. Methodologies such as the Mora-Vahrson and HSQI are based upon a set of hypotheses, indicators, parameters, and criteria, either deterministic or probabilistic, but representing mostly the features of regions in which they were conceived. Therefore, it is not recommended to be directly applied without an adequate adjustment to the local context. The application of the HSQI here is a perfect example of this last one. So general recommendations. The geometry and anthropogenic slope can be adequate parameters to assess its potential instability. It must be used considering how their spatial variations vary and affect the safety factors. Accurate seismic and precipitator indicator values when applied in these methods can increase their accuracy in determining the susceptibility of a slope exposed to these triggering events. The Mora-Vahrson is a perfect example of this. As it has been shown that depth of the water table creates a high sensitive to instability scenarios. Therefore, it becomes highly important to have a good understanding of its geometry and hydrodynamics and its lateral and seasonal variations. And the use of cohesion and friction angle is not recommended to analyze rockfall topples and other rock mass instability scenarios. And thank you.
Thank you very much, Randall. It was really nice to have such kind of presentation. Let's see if I have any questions. Please provide your questions to the chat session of Zoom app in order to be answered from the keynote speakers. Just before starting the questions, I would like to ask you a question. Did you try to apply it in a different area rather than solely on the area that you're applied?
No, the project was focused on this area as we wanted to see if it could work in this specific scenario. It has been priorly applied in other highway corridors by Carlos Arturo Moreno Ceballos when in the original proposal. It was in a highway in Colombia. The name of the highway eludes me right now. And it was also applied here in Costa Rica by Mariela Ocampo in 2016. Both other regions were highway, yes, but were not as vegetated, rainy, or weather as this one. So I have not, but the method itself has.
Okay, yeah, because it seems really interesting and promising, I could say, for decision making and just for including these parameters and these kind of models in a more holistic assessment. So I think there is a lot prominent on that. Okay, just to see if there are any questions, please, I will repeat myself. Provide any questions in the chat.
To answer your question on the Mora-Vahrson methodology, Randall, can you just stop sharing your screen? Perhaps we can.
Of course. There you go.
Yeah. Mora-Vahrson has been applied in many areas, virtually in all Latin America, and parts of Africa, Middle East, even in Japan, with different degrees of success. Just type Mora-Vahrson in Google, and then you will have about, I don't know, 50 to 70 pages of comments. Of course, not all of them very positive. There are critiques and suggestions as well. But in general, if I could make a general qualification of it, it is all areas involved about 75 to 80% successful. There is a lot of room for improvement, of course, and that I believe that we are already working with that with Engineer Saborio, and I see Wilhelm Gunther Vahrson with the audience. I hope that he will rejoin us in advancing work. We believe that from the climate circumstances, there is a lot to be improved. And we are requiring little by little to have more resolution and perhaps advancing to a stage that might yield microzonations more than macrozonations. So these are the main goals of what it is expected from the methodology and its development in the near future.
Yeah, I think it's a really promising methodology, and looks like the results are really comparable with other methodologies that they have been used for decision making. So I think a lot more have to come. I can't see any questions. So in order to conclude, Today, I would like to both thanks our presenters, Professor Sergio Mora and our geologist, our YEG geologist, Randall Carballo. It was a pleasure to host you both here, and our pleasure to have you in presenting your work. I hope on the following months to have the possibility to meet in close after the whole COVID situation will get better. Hopefully to a conference or to a IAG meeting. So once again, thank you very much. Thank all the attendees for being here. For your information, you can find the current webinar after our finish line in the YEG YouTube page. So once again, thank you very much and stay tuned for more actions from YEG. Thank you.
And
Thank
thanks to
you
you.
for the efforts and work to organize these webinars. One more thing that I would like to add is that if the audience requires literature, bibliography on the study cases that we have performed, they can write to you, and then you can readdress us or write directly to us, so we can offer publications and technical reports on the matter.
Definitely. That's really nice. Thank you very much. Thank you. Thank you, Professor Mora Castro. So see you all. Good night.